Hello, I'm Matt Gruber. I'm here virtually at 3D Experience World 2022 to present an instructional course. So what we're going to look at is a unique way to design with long structural elements that bend and twist along the surface of an assembly. So we're going to recreate these stringers that run along the surface of this wing. So we could use for each one of these stringers a swept boss feature that we would run this cross-section along a surface intersect curve and input a twist. But we're going to see that there's a better way to do this that produces better results in a way that's, first of all, very compact. So you can see in this feature manager tree, all these stringers are done in minimal steps. And the other thing is that the way to accomplish this with this wrap feature, the way the wrap lays these stringers along the surface is a natural way in which they can be installed. So that's what we're going to take a look at today. We're going to use this example assembly that I made here, which is a RC aircraft with a wingspan of 12 feet. It's designed based on the SAE Aero design regular class rules from 2016 to 2020. So with the structural layout here, that's pretty common for RC aircraft. The role of the stringers is they take load from the wing skin around them and accumulate that into the stringers, and then the stringers move that into the ribs, and the ribs move that into the aluminum wing box, which is part of the overall skeleton of the aircraft. So this is what it looks like inside the wing box here. Now the stringers are 1/2 inch by 1/8 inch balsa wood strips pretty frequently, and the skin could be like a vacuum formed plastic or a draped over a shrink formed plastic coating that adheres to the stringers and the ribs. But the techniques that we'll learn to design these rectangular cross-section stringers are intuitive to expand to the general case of other types of cross-sections. For instance, in commercial full-size aircraft, often the wing box is, the spars will extend all the way to the wing surface, and then so the stringers, which will be more like this aluminum T-section or another type of extrusion, those themselves will often bend and twist along the wing surface. And I'm sure there's lots of other applications where long, thin structural members bend and twist along surfaces. Before we get into the course, I'll just introduce a bit about myself and my background. I've been designing in CAD since about 2011. I was working at the time in science in Alaska, and in my spare time I designed this bicycle hub. When I returned to Montreal, I did an engineering degree at Concordia University, and that's where I was introduced to team design projects in SolidWorks like this steam car. At that point I was hooked. So then there was this wind tunnel project, and being inspired by how neat it is that airplanes and helicopters are used in Alaska and BC, I joined the SAE Aero design team where we designed and built RC aircraft like this. My engineering work experience has been a year at Bombardier in internships in loads and stress, and then 4 in Bell Helicopter in airframe stress on the 525 model. Working those years in analysis alongside designers, I now want to work on the design side of structures. So as part of that path, in March of 2020, I started a tutorial channel on YouTube with SolidWorks. And so here I am with a SolidWorks instructional course. Now, during the physical assembly of this wing, what's going to determine the shape and location of the stringers is these cutouts in the ribs. So we're going to lay the stringers into these cutouts. The initial shape of the stringers is straight, and then we flex them into these cutouts, and that determines their shape at the end, the twist and bending. So they come in like that. Now that's opposed to the design process where first we design the stringers. So we design this part here, and that determines the shape and location of the stringers in the design. And then the cutouts on each rib are downstream information from that. Let's take a look at one of these stringers in real life here. This is the stock material. It's straight and it's 1/2 inch by 1/8 of an inch. And we can see that along the 1/8 of an inch side, it's really easy to bend. It's really flexible. And it's easy to twist along its length as well. But along the 1/2 inch side, it takes quite a lot more force to get any bend out of it. And the deformation is going to be pretty limited before it cracks. So let's take a look at those bending and twisting directions in SolidWorks. So here we have a bend only, that's a sweep. And we can see that that's easy to model, and in physical reality that'd be easy to bend. A twist, we can see, so that's another sweep that just has a twist input. And so to model that, and in reality the stringer can accomplish either one of these with very little resistance. Now if we see a bend and twist, so this one is a sweep that has a 20-degree twist input like this one. And you might initially think that this doesn't look like it's physically all that difficult to twist and bend the stringer with this center line constant here. But I mean, we can visualize if we up this angle, let's up it all the way to, let's say, 110 degrees. I mean, at that point, we can see that at one point it's bending along its hardest to bend direction. So even though this one only has 20 degrees, if we put just 20 degrees in here and then bend it, a little bit of that bending is taking place along its harder to bend direction, that 1/2 inch direction. And so here you can see this sweep is forcing the center line to be constant. That's in contrast to a wrapped stringer. So if we take a look, this is like a surface that kind of looks like a wing surface. And we're going to learn how to use the wrap feature to generate stringers like this, where it's wrapped onto the surface in a way that as it twists, its downwards direction of bending shifts. So it twists and the downwards direction of bending shifts to the right here. So we can compare with this would be like a swept boss stringer that adheres onto this surface, and the wrap, we can see how much of a difference it is here. So we know our goal now. We want to design the stringers so that they bend along their least stiff axis while twisting. So let's go back in time here with this assembly to just before the stringers had been designed and their cutouts are not in as well. So we're going to design those. So the wing is a top-down assembly with this surface part as an external reference for all the parts within the wing. So that's going to include the stringers. So I'll input a new part here. Just name it to example for wrapping. And we're going to float it and then mate it to the origin aligned. And then we can save it in an external file in here. And this we're going to edit in context. So let's do a walkthrough of the swept boss first. So first we're going to, in context, go and grab the surface references. So we can either grab them straight from clicking them there, or we can grab them from the bodies list within the part, the reference surfacing. So we'll take these two, go to surfaces and offset it. So 0 inches creates a copy, a linked copy with, you can see this arrow on the surface denoting an external reference. So once we have those, we can open up our part. And so this will be our external ref surface. Now, let's say we're just going to first create a stringer using the swept boss and then also the wrap. Let's say about in this position here, from looking from the top view, the stringer will come in and approximately lie there. So call this a stringer layout. And so if we're going to do a swept boss first, let's create a plane along here, perpendicular to the top plane. And that'll be the center line plane of our swept boss stringer. So then we can go in here and create the intersection curve within this plane where our stringer is going to go across. So then we need a plane for our cross section. So we can go into planes and grab there and this point. And looks good. So let's rename these. And this is the plane cross section. So in here, that's going to be our 1/8 of an inch by 1/2 an inch. So we'll start with something like that. Make it tangent here, and I'll put in the dimensions. So 1/2 inch by 0.125 inches. And just hide this. I put in a point here that we can use. So we've got that in position. Now we can use a swept boss. So from here, do a swept boss along this path. And we can see it going in. But we can see that it needs a twist input because it started off tangent over there and it ended up not so tangent at the end. So we can go into here and under options we can put a twist value and we can just eye it for now. So if we take a look down the normal, the other direction, we can see that the center line stayed constant along the whole stringer here. So we're going to make a wrap now, a wrapped stringer, and compare what we get. So for our wrapped stringer, first we're going to make a sketch in the top plane, and from the stringer layout, not this one, we'll hide that, show the stringer layout. From this one, which is in the top plane, we're going to do an offset entity, and if we do it bidirectional at 0.25 inches, that'll make a sketch that represents what the stringer will look like. And let's hide the sweep for now. So we'll just go and close these. So we have a sketch that represents a flat, straight stringer, sort of the projection of it. You can exit that. And what we can do is take a look at what the wrap feature does. So let's hide these two planes, we won't need them. And now let's hide this as well. So the wrap, if we go to the features and do wrap, so if we're going to go on this face, we can see it's projecting. It's not exactly projecting, it's taking this sketch, this closed contour sketch, as if it were sort of like a sticker. And if we put high preview detail, it's taking it sort of like a sticker and pasting it to that surface. We can see that the center line is not constant in this case. It does bend in a different direction as it twists. So because we're wrapping onto a surface, the only option we have here is to scribe. So if we were to scribe, what that would do is sort of delineate faces here. And we can, however, instead, let's get rid of this wrap. What we can do is, let's thicken this surface because we can emboss onto it as a wrap option as well. So if we thicken this, we're going to thicken it outwards. And it doesn't really matter how much, so 0.10 inches is okay. So we have this solid body that we can now wrap onto in a different way. So if we go to this sketch again and wrap, and we're going to use emboss onto this surface. Once again, we'll get a better preview. Now this is an analytic method here. It's a spline surface. Sorry, it's not analytical, it's a numerical spline, because this option here will only work on certain shapes that have a closed form solution like a cylinder, whereas this is a general case of a spline surface that we're going to use. So we're going to use emboss, and the stringer is 1/8 of an inch thick, so we're going to paste on this sticker as if it's not a flat two-dimensional sticker, but a 1/8 inch one. So it'll take a bit to crunch that, and then we can see it ends up here, and this entire surface has had that stringer added to it. So you can imagine if we want to just have the stringer, what we could do is go back to here and do a cut with surface, and we'll cut this way. There we have it. So that is a stringer, and so let's show the sweep again. So we can see they're a bit different. They got generated from the same layout, but if we visualize the surface, let's give them some different colors. So the sweep, give it blue, and the wrap, let's give it green. Let's change its name. Let's view this plane again so that we can look down it. So here we can see a difference here. If we look at the center line, the blue one, the swept boss, stayed at a constant center line. So one problem with our sweep here is that this twist comes in at a constant rate, and that might not be how the stringer actually wants to curve. So one thing we can do to make this, to get something with the same center line as this swept boss, but to twist with the normal constantly in the surface's direction, we can do something where, so first I'll create some copy surfaces of the outer surface there. And with this surface, we're going to take the layout and we're going to make another sketch in the top plane, the line that's parallel to it. And we'll make this about 1/4 inch to the other side of it, which we can also take a reference from here. So maybe the midpoint of that one. So with that, we're going to insert a split line on this surface. So that's going to delineate the faces here. And so let's just hide these two. And there's a good tool for that, this offset on surface. So we can choose this line. And so we've got two options here, the geodesic offset, which is going to be an offset that takes a curved measurement, or this Euclidean offset, which is through free space. And since we want a 1/2 inch flat surface at the top, let's do actually 0.5 inches. So we have that 3D sketch on this surface now. And we'll get out of that. And then we can just do a lofted surface. We can even reference that edge and that line that we have there. And so that will be, as we hide these, that will be a 1/2 inch across the whole way along as it's twisting. And we can thicken it. 0.125 inches. And so now we can compare these two. So they're pretty close, but this one here is, it's not a manual constant rate of twisting. It's twisting the natural amount for that surface. So we can also improve our wrap in the same type of way. So if we notice, hide this one, the wrap, it doesn't exactly have a square cross section, or rectangular cross section, because it is curving on that top surface with the surface that it's being wrapped to. So I mean, compared to the length of that stringer and the width of it, it's not curving that much in this direction. We could probably use this wrap as it is in this case for the rib cutouts. But I mean, we could, if we really wanted to, do the same type of thing. So if we wanted to, we could do a lofted surface just from one edge to the other, and thickened that as well. This way, not merge. And let's make this one blue. Now for the wrap, the difference between the square cross-section one and the curved one, it's hardly different for this light curvature of the wing. There are areas on the aircraft though where you might have to take a different approach. Like for instance, on the aft fuselage here, that curvature is tighter than the wing. So if we take a look at the aft fuselage portion of the H-tab here, yeah, we can see that this might be a little too curved for actual use as our cutouts. So that might be a place you might want to use that split line and surface Euclidean offset. So we can take a look at this part here. So in this part, we're going to take the old layout for the wrapped stringers. That's a sketch in the right plane. And first we'll make another sketch in the right plane that's so 1/4 inch inwards for both of these. I'll go inwards for both of them. And we'll take the surface reference, 0 inches, and from this sketch, so that's approximately where the inner edges of the wrap stringers are. So let's hide the wrap stringers, and we're going to input a split line on this face. And from there, so these are the inner edges of those stringers. And now if we want a 1/2 inch offset on the surface, we can do this. And that'll be one 3D sketch. And then we do another one here to the outside. So that should be good. And then from there, we can just do lofted surfaces here. There. That's one of them. Another one is here. So now we can hide this surface and thicken these. Surface thicken to the inside 5 inches, and same with this one. So that could be a way to get square cross sections on stringers that they definitely twist, but they might not necessarily bend as much as they have curvature in the 1/2 inch direction there. So we can compare with the wrap. I mean, yeah, the wrap might be too curved, so we might go with these this method for that type of application. Let's replicate this stringer for a whole group of wrapped stringers in the assembly. And in this case, I'm doing one part for the stringers that go on the top, and then a different part for the stringers that go on the bottom. So we'll just do the example for the ones that go on the top. So the layout, let's go back to this point. So we'd be putting in more lines. Something like that. So then we'd be putting in the offset sketches. So 0.25 bidirectional. And we would close them all. Continuing like that. So the layout can look like this. Now the wrap, you can see it's all in one feature here. It can look like this. So we're taking those offsets and applying them to that surface. And what we're wrapping is, so that sketch look like this. The surface cut, that will look like this. So once we cut, we'll have the option to keep only certain bodies or all bodies. The last step is this one I did within the wing assembly. So the last step are these cut extrudes that cut off the ends. For instance, you can look from above. And you can hide certain parts in here. Really, these are just referencing the rib, so you can hide the other stringers and all that when you're going in here and cutting out the ends of the stringers beyond the last rib outboard that they'll intersect. So there's cutting off the tips and also cutting off, so in this case it's separating the wing from the aileron, and there is trimming the fuselage part from the wing part. Once we've moved from a single stringer to multiple, like these, now we're ready for rib cutouts. So like if we take a look at, for instance, this rib, so we'll have to edit it and go into its right plane. And what we can do is just go grab, so if we find the stringers, we can go into their bodies and just grab the bodies and do an intersection curve. We could do that for the bottom too, but I just want to illustrate one thing first, which is that, so these stringers, for now I have them running right along the surface of the wing. So if we try to use an extruded cut here and do through all, it tells us it's unable to create this because it results in zero thickness geometry, because the sketch is intersecting right along the same extrude sketch as the rib, because that rib is referencing the same surface. So we could manually go into that sketch. Press Control Q, it'll come back. So we could go into these sketches and just extend them. Or there's another trick we can do. So we'll keep this sketch here and go into the stringers part, the top stringers. And instead of having this surface be a copy of the wing outer surface, we can just extend it. So I found in this case that 0.01 inches, like a 10 thou, can work for us. So let's just make sure it's going outwards. Yeah, it's outwards. And now, if we get out of this, we can see they're just a little bit above the outer surface. Now if we go into this rib and Control Q that rib, go into its sketch. Now they do not, these top intersects of the stringers doesn't intersect the extrude sketch of the ribs. So we can use this for an extrude cut through all both. And that works. And we can also go and grab the stringer's bottom bodies here, the solid ones. Intersect. And exit that. There we go. Just a quick note that even though, so these stringers come in at slight angles to the right plane of the ribs, and if we open up this rib, we can see that with the cut extrude in its right plane, that would fit perfectly only if the stringers are perpendicular to that plane. But I mean, in practice, if you were actually going to do these cutouts at the exact angle the stringers are coming through, you could use the cavity feature. But to actually manufacture these ribs, generally people are using 2-axis laser cutters, or if they were made of metal, it could be a water jet cutter. And those can't do cuts at oblique angles to the surface here. So, I mean, in practice, the balsa wood stringers, just if there's a slight gap or overlap as you put them in at an angle, they just sort of crush into place, and any gaps get filled with glue. So, I mean, as long as the angles aren't, as long as the stringer's not coming in at like 30 degrees or something like that, they end up fitting pretty well. Another caveat is that sometimes the wrap can fail to calculate. I find that if that's the case, often you just have to very slightly adjust the layout sketch. The lines just, you can move them even just like 1/100th of an inch or something, and sometimes that can get it to solve. And another thing is that, so if it keeps on failing to calculate, one thing you want to make sure of is that about the center of the sketch pattern that is going to be wrapped, like this sketch pattern, is approximately in the middle of the surface. So something you can do that gives you a better chance of having the wrap solve is if you have sort of a complicated surface like this where there's faces that have lots of corners and pointy ends sticking out, you might want to just trim it a bit before wrapping. In that case, this is the surface that worked for wrapping this here. Another thing specifically for wings, if you have a trapezoidal planform and just geometric washout for a tapered wing like this one, then you don't necessarily need the wrap feature, because along constant chord lines, constant percent chord lines, there is no curvature along these lines. So you can arrange the stringers along those percent chord lines and then they're all straight. So you can just use an extrude with a twist. Now if you want in a wing like this for the stringers to be perpendicular to the ribs, then you can use the Euclidean surface offset and the lofted thickened surfaces like we saw. But yeah, if you don't have the curved planform or a changing airfoil cross section, then you might not need to use the wrap. Now another caveat is the wrap as a numerical solution seems to recalculate sort of differently than other features. So if you rebuild with Control Q inside a part with a wrap, it seems to recalculate it no matter if the inputs to the wrap are unchanged. So it could refresh downstream of there based on a potentially slightly different wrap solution. So in this assembly, I kept the wraps pretty much at the bottom level of the top-down assembly. But in the higher level assemblies, if you Control Q within that assembly, it seems like the wrap doesn't recalculate unless the inputs to it, like the surface or the sketch that's being wrapped, are changed. So in summary, if a design calls for long structural elements that bend and twist along a surface, and if we want them to only bend in their minimally stiff axis, then the wrap feature can accomplish all of this with the efficient and elegant design flow and feature manager tree. Now, if the curvature is tight along the thinner direction, then we can use the Euclidean surface offset and lofts from the split lines. Thank you for watching. Thanks to SolidWorks and SolidXPerts here in Montreal. If you have any questions or want to reach out for networking, or if you know of other ways to go about this type of design, you can reach out in the 3DX World online speaker community center or through email. And if you're watching live at 3DX World, please fill out the survey. And yeah, you can check out my YouTube channel. And yeah, hopefully next year I can join in person. At least my beard will grow at a more manageable pace over 45 minutes in person. So thank you and have a good day.